in this question, we're given some sort of curve which a particle moves along. And we've got that curve parameterised via 3 equations that depend on time. Okay, so think of this as sort of each component equation. If you wanted to write this as a vector in terms of vector functions of one variable, you could write it something like this in terms of i's, j's and k's. Or if you wanted to write it as an ordered triple, which is sometimes the notation I use just without i's, j's and k's, you could write it like this, okay? Now, before we even look at the questions, let's actually try to determine the curve that this parameterization represents, okay? Now, hopefully, if I cover up, say, the x of t, and I just look at these 2 functions, we've got a cosine 3t and a sine 3t in there. So if we were just to plot, say, in the yz plane, the curve associated with this, what do you think it would be? It'd be a circle, radius 2, centred at 0, 0. Okay? So if I just ignore that one, this is going to be a circle in the yz plane, centred at 0, 0, and I guess the motion would be an anti-clockwise direction as t increased. Let's add in this extra function now, this extra component, x of t equals e to the minus t. Well, okay, what happens as that, let's say t starts at t equals 0 and t increases. What happens to e to the t? It's positive and it decreases. Okay? So what you've got, essentially, is something that's rotating sort of from the view of the yz plane and decreasing along the x-axis. So in this picture, this would be the x-axis, this would be the y-axis, and this would be the z-axis. So it starts here. When t equals 0, e to the 0 is 1. Okay, so out here. And it'll just go and spin around. The curve is called a helix. Okay, so this would be the direction of motion, I guess, or the path travelled. Okay, so we're asked to do 2 things in this question. We're asked to determine the velocity vector and the acceleration vector. And in the second part, we're asked to find the magnitude of the velocity and acceleration vector at the instant when time equals 0. Okay, so this is known as a helix. Now, how did I produce that? Well, I just used Maple and a command called space curve in the plots part. Okay, so if this is our position vector for any point on that curve, how do we determine the velocity vector? Can anyone remember? Differentiate, right. Okay, so we can form the velocity vector. So let's just denote it by, say, v of t. It's just the derivative of our position vector. Okay, so how do we differentiate a vector function of one variable? Well, we just differentiate the component functions separately. Okay, so what's the derivative of e to the minus t? Well, it'll be minus e to the minus t. Differentiate 2 cosine t. Well, cosine's going to go to a minus sign, and that 3 is going to come to the front. And differentiate 2 sine 3t. Well, sine's going to go to cosine, and that 3 is going to come to the front. Okay, so note, that's our velocity vector, if you like. Okay, the next part is to calculate the acceleration vector. So for that, what we do is we take the velocity vector and differentiate it again. So let's call that A of t. Okay, so let's just take this velocity vector and differentiate that in a component-wise fashion. So the e to the minus t is going to just become e to the minus t. Sine's going to go to a cosine. The 3 is going to come out the front. And the cosine's going to go to a negative sign. So note again, our answer for the acceleration is a vector. It's a vector function of one variable, time, t. So it's pretty easy so far. Part B asks us to calculate the magnitude or the lengths of these velocity and acceleration vectors at the instant when t equals 0. Okay? Now you can do these one of two ways. You can either calculate the magnitude of each vector, the v and the a, and then plug in t equals 0, or you can plug in t equals 0 and then calculate the length. I'm going to do one way and then the other one the other way. Okay? Now, the magnitude of the velocity. Can anyone tell me what would that represent? The magnitude of the velocity. The speed, right? Okay? And it should be a number, right? Not a vector. Can we talk about magnitudes, lengths? It's definitely a number, not a vector. So I'm just going to calculate the magnitude for any point t, and then I'll plug in t equals 0. Okay, so how do I take the magnitude or the length of a vector? Well, I look at the component functions, I square them, add them together, and take the square root. Okay, so up here it's going to be minus e to the minus t squared. And then here we've got minus 6 plus minus 6 sine 3t all squared plus 6 cosine 3t all squared. Okay, now this is a bit nasty with the square root sign, but if I look closely, I'm going to get a sine squared 3t and a cosine squared 3t with the same coefficient, both 36. So I can simplify using cosine squared plus sine squared equals 1. Okay, so this is going to become something like e to the minus 2t. Using cosine squared plus sine squared equals 1. These two terms, when I expand them, are going to become 36. So at the point t equals 0, I can just calculate from here. I'm going to get e to the 0, which is 1. So I'll just get root 37. Okay, that's one way of doing that problem. Let's do it the other way. I want to calculate the acceleration at t equals 0. So I'm actually going to go to the acceleration vector, plug in t equals 0 first, and then I'll get the magnitude or the length. Okay, so here's just the value of the vector. So e to the 0 is going to be 1, yes. Minus 18 cosine 0 is just going to be minus 18. And minus 18 sine 0 is just going to be 0. So the length or the magnitude is just the length of this vector here. So it's 1 squared plus negative 18 all squared plus 0 all squared. Add it together and square root it. Okay, so I'll get this.